So in exercise number 1, section 5.1, is lambda is equal to 2 an eigenvalue of the matrix 3, 3, 2, 8, y or y not? We said that 2 is an eigenvalue of the matrix. Let us say this one is A, if and only if we could write A multiplied by x is equal to x for some x not equal to 0. Now if we rewrite this one, so from here we have ax is equal to x, that means ax minus 2x is equal to 0. If we take x as a common factor, so we have a minus 2i multiplied by x, this will give us 0. So if we could solve this one, a minus 2i, this one represents a matrix multiplied by a vector is equal to 0. We want to find such x. If we multiply by this matrix, we get it is equal to 0. So first let us find what is a minus 2i. This is just the matrix A, 3, 3, 2, 8, minus 2i is the identity matrix multiplied by 2, so 2, 0, 0, 2. This will give us 3 minus 2, 1, then 3, 2, 8 minus 2 will be 6. Now if we do row operation for this matrix, it is clear from here that the second column is just a multiple of the first column, where v1 is equal half v2. So the columns are linearly dependent, and this equation ax minus 2x is equal to 0 has a non-trivial solution. That means there exists x such that ax is equal to x. And so from here we conclude 2 is an eigenvalue of A. So let us write here. The columns are linearly dependent. So hence A minus 2ix is equal to 0 has a non-trivial solution. That means x is not equal to 0, and 2 is an eigenvalue of the matrix A. In 7 we can do it the same way we did in 1. So is lambda is equal 4 is an eigenvalue of this matrix? If so, find one corresponding eigenvector. So just here we need to find what is the corresponding eigenvector. For 1, just we need to know if 2 is an eigenvalue of this matrix or not. So in the same way we did, first we find a minus 4i, which is this matrix. We subtract 4i. Then we try to solve this one, a minus 4i multiplied by x is equal to 0. We are looking for non-trivial solution. So after doing row operation, we get this matrix. This is the last one. So the system, since we have the third row, we have all of them is 0. That means we have a non-trivial solution, and this leads us to 4 is an eigenvalue of the matrix. To find what is the eigenvector, just we need to find the solution, which is in the form x3 multiplied by minus 1, 1, 1. So from here, any vector in this form is an eigenvector corresponding to lambda is equal 4. You can choose whatever value for x. So for example, when x3 is equal to 1, minus 1, 1, 1 is an eigenvector. If x3 is equal to, then minus 2, 2, 2 is an eigenvector, and so on. In exercise 3, is 1 for an eigenvector of -3, -3, 1, 8? If so, find the eigenvalue. So if we are asked to find or to know if the vector is an eigenvector of the matrix, that means the vector, if we say this one is V, this one is A. So if we can write AV is equal to lambda V, where V is not equal to 0, then we conclude from here this V is an eigenvector of the matrix A. So now let us find what is AV. So our matrix A is -3, -3, 1, 8, multiplied by the vector 1, 4, which is equal to -3 plus 4 will be 1, -3 plus 32, which is 29. Could we write this one as lambda multiplied by 1, 4? This one is 1, this one is 29. We couldn't write it as lambda multiplied by the vector v. So this one is not equal to lambda multiplied by the vector 1, 4. So from here, no, v is not an eigenvector, because we couldn't write it as this form. So now for 5, we have also another vector, which is 4 minus 3, 1. Is this vector is an eigenvector for the given matrix? If so, find the eigenvalue. So first we need to check, multiply this matrix by the vector, this one, v. We get the result, it is equal 0, 0, 0. So could we write this vector as lambda multiplied by 4 minus 3, 1? Yes. If we choose 0, then multiply by the vector 4 minus 3 lambda, that's me, minus 4 minus 3, 1. That's mean our lambda is equal to 0. So this vector is an eigenvector for this matrix, and we have that the lambda is equal to 0 corresponding to the eigenvector 4 minus 3, 1. In exercises 9 to 16, find a basis for the eigenspace corresponding to each listed eigenvalue. So we need to find the basis for the eigenspace corresponding to the given eigenvalue. So for 9, we have the matrix A, we have the eigenvalue 1, then we have another eigenvalue which is 5. So when lambda is equal to 1, we have the eigenspace can be written as A. We know that A minus lambda I multiplied by x is equal to 0. So our lambda is equal to 1. So from here, A minus ix is equal to 0. We want to find the basis, so that means we need to solve A minus I multiplied by x is equal to 0. Our A is 5201. I, we know it 1001. So this is 5 minus 1, 4. Then 2, 0, 0 multiplied by x is equal to 0. So from here, that means we need to do row operation to find what is what is our x. So after doing row operation for this one, we get 4, 0, 0, then 0, 0. So here 1, 0, 0, 0. So from here, x1 is equal to 0, x2 is equal to x2. So if we want to write x in the general way, x1 0, x2 is equal x2. So we can write it as it is equal to x2 multiplied by 0, 1. So since only we have this vector, so the solution in the general form of x2 multiplied by 0, 1, so the basis is equal to the unique vector, which is 0, 1. We do the same thing when lambda is equal to 5. So when lambda is equal to 5, we need to find a minus 5I multiplied by x is equal to 0. So our a is 5201. If we subtract 5 from this one, we get it is equal to so 5 minus 5 will be 0. These two remain the same, 0 remain the same. And then we have 1 minus 5, this is minus 4. Multiplied by x is equal to 0. So now we need to solve this system. We have 0, 2, 0, minus 4, 0, 0. So if we do row operation for this one, we can swap between these. Divided by 2, we get 1, minus 2, 0, 0. So from here, if we write this one as a general form, x is equal x1, it is equal to x2. x2 is a free variable, so it is equal x2. So this is of the form x2 multiplied by 2, 1. So the basis is equal to this vector, which is 2, 1. So for lambda is equal to 1, we need to solve a minus I multiplied by x is equal to 0, find the vector or the solution. Similarly, when lambda is equal to 5, we need to solve a minus 5I multiplied by x is equal to 0. Doing the row operation, we find what is the basis. And then for 11, 13, and 15, all of them we do it in the same way. Here we have a matrix A, we have lambda is equal to 10. So we need first to find a minus 10I multiplied by x. After finding the matrix, we do a row operation, find what is the solution. Similarly, here for 13, we have 3 lambda is equal 1, lambda is equal 2, lambda is equal to 3. First, we find when lambda is equal to 1, find the corresponding vector. Then, when lambda is equal to 2, we do the same thing, just we change lambda, we find what is the vector. And lastly, when lambda is equal to 3, we find a minus 3I multiplied by x is equal to 0. Here we get the vector, this one, which represents the basis for the matrix, for the eigenspace. For 15 also we have a matrix, we have lambda is equal to 3, we need to find the basis for the corresponding eigenspace. So first we find a minus 3I multiplied by x is equal to 0. We do row operation. Here we find that we have two free variables, which is x2 and x3. So that means the basis will be contained of two vectors, which is corresponding with x2 and corresponding with x3, which is both of them are free variable. So keep in mind that not always the basis will be one vector only. It may be 2 or 3. It's depend on the matrix and the eigenvalue. In 17, find the eigenvalues of the matrices in 17. So here we have our matrix, this one. See, this one is a triangular matrix, which is an upper triangular matrix. And we know that for the triangular matrix, the eigenvalue are the entries in the main diagonal. So from here, lambda is equal 0, lambda is equal 2, lambda is equal minus 1. All of them will be an eigenvalues of this matrix. First, check your matrix if it is a triangular. Then you can choose all entries in the main diagonal, and that will be the eigenvalues. Now for 19, for a is equal this matrix, find one eigenvalue with no calculation, justify your answer. So we need to find one eigenvalue without calculation. We see here the first column, the second column, the third column, they are linearly dependent because we can find the second column by subtracting this one and this one. We can find the first column by subtract this one and this one, and so on. So the columns are linearly dependent. that means A is not invertible. If A is not invertible, that means 0 is one of the eigenvalue. So let us write it here. The columns are linearly dependent. That means A is not invertible. And hence 0 lambda is equal to 0 is an eigenvalue. We don't say that every eigenvalue is equal to 0, no, just lambda is equal to 0 is one of the eigenvalue. It may be another eigenvalue which is not equal to 0. But from here, if the matrix is not invertible, we can say that one of the eigenvalue must be equal to 0. In exercise 21, A is n by n matrix. Mark each statement true or false, justify each answer. So A, if Ax is equal lambda x for some vector x, then lambda is an eigenvalue of A. We say that Ax is equal lambda x for x should be not equal to 0 because we don't want a trivial solution. So this one is false. X should be not equal to 0 because we want a non-trivial solution. So B, a matrix A is not invertible if and only if 0 is an eigenvalue of A. This one is true because if the eigenvalue is equal to 0, A cannot be invertible because we have a 0 in the main diagonal maybe. That means we find the determinant will be equal to 0, so this one is true. Then for C, a number C is an eigenvalue of A if and only if the equation A minus Ci multiplied by x is equal to 0 has a non-trivial solution. This one is an eigenspace for this matrix corresponding to an eigenvalue lambda is equal to C, so this one is true. D, finding an eigenvector of A may be difficult, but checking whether a given vector is in fact an eigenvector is easy. This one is true, because if we are given the vector V, and this question say is V is an eigenvector, just we need to multiply A by the vector and check if we can rewrite it as lambda V. But if we ask to find the eigenvector, it will take long time because we need to do some row operation for the matrix. So D is true. Now for E, to find the eigenvalues of A, reduce A to echelon form. This one is false because it is not the way. So E is false. In 23, explain why a 2 by 2 matrix can have at most two distinct eigenvalues. Explain why an n by n matrix can have at most n distinct eigenvalues. We know that for n by n or 2 by 2 matrix, if we say this one has more than 2, that means it has 3 eigenvalues. That means these 3 eigenvalues correspond to 3 different eigenvectors. But this vector must belong to the two-dimensional vector space, and the 3 vectors will be linearly dependent. And our vector in 2 by 2 matrix, if it has 2 distinct eigenvalues, so they should be linearly independent. So if we want to write this one here as this one, so if A is a 2 by 2 matrix with 3 distinct eigenvalues, so if we have, for example, lambda 1, lambda 2, lambda 3. Each lambda of this one will be correspond to different eigenvectors, which is v1, v2, v3. And this one will be impossible since the vectors belong to two-dimensional vector space, because we have here 2 by 2 matrix, in which any set of 3 vectors are linearly dependent. We cannot say we have 3 vectors corresponding to 3 different eigenvalues for 2 by 2 matrix. Similarly, if we have n by n matrix, we cannot have more than n distinct eigenvalues. In 25, if lambda be an eigenvalue of an invertible matrix A, show that lambda power minus 1 is an eigenvalue of A inverse. Hence, suppose a non-zero x satisfy Ax is equal lambda x. So we want to show that if lambda is an eigenvalue of invertible matrix A, then 1 over lambda will be an eigenvalue of A inverse. So now if we assume lambda is an eigenvalue of A, then that means there exists x such that Ax is equal lambda x. Now, since our matrix A is invertible, it is given that A is invertible, then we can multiply this matrix by A inverse. So A inverse Ax is equal A inverse lambda x. We know that A inverse by A is the identity multiplied by x, this will give us x. Now A inverse lambda x, this one is a constant, so we can take it here by the properties of the matrix A inverse x. Now if x here written by lambda A inverse x, for x is not equal to 0, and A inverse is invertible, since A is invertible, then that means lambda is not equal to 0 because A is invertible. So from here, if we multiplied both sides by 1 over lambda, or lambda power minus 1, so lambda minus 1x is equal lambda power minus 1 lambda A inverse x. This will give us lambda power minus 1x. 1 over lambda multiplied by lambda, this will give us just 1. So here we have A inverse x. Now, since we have the form A inverse x is equal 1 over lambda x, that means lambda power minus 1 is an eigenvalue of A inverse. So from here, lambda power minus 1 is an eigenvalue of A inverse. Here, why we say that lambda is not equal to 0? Because we cannot divide by 0. Because lambda power minus 1, it is just 1 over lambda. And we want to divide by lambda, that means lambda should be not equal to 0. Why we say lambda is not equal to 0? Because here x is not equal to 0, and A inverse is invertible, since our A is invertible. So this one is not equal to 0, and lambda cannot be equal to 0. In case lambda is equal to 0, that means all this part will be equal to 0. So that's why x is not equal to 0, lambda is not equal to 0, A inverse is invertible. In 26, show that if A square is the 0 matrix, then the only eigenvalue of A is equal to 0. So if A square is the 0 matrix, it is given that A square is the 0 matrix. So let us say let A square be the 0 matrix. Let A square is the 0 matrix. Now if Ax is equal lambda x for some x not equal to 0, then if we multiply both sides by A, so it will be Ax is equal A lambda x. So this one is Ax is equal A lambda x. we can rearrange this one lambda as a constant, so here we have ax. Now we know that ax, it is just lambda x, so this one we can replace this one by this one, so this will give us, so here we have a square x, it is equal ax, we will replace it by lambda x. What is this? This one, a multiplied by a will be a square. Here we have x, so lambda multiplied by x, ax it is just lambda x, so lambda multiplied by lambda x, that means lambda square x. Now since x is not equal to 0, we said from the beginning x is not equal to 0 and a square is the 0 matrix, that means this side should be equal to 0, because a square is the 0 matrix, and 0 multiplied by any vector, 0 matrix multiplied by any vector x, this will give us 0. So if x is not the 0, so that means lambda square should be equal to 0, and from here lambda is equal to 0 is an eigenvalue of the matrix A. 27 show that lambda is an eigenvalue of A if and only if lambda is an eigenvalue of A transpose. So that means lambda is an eigenvalue for both A and A transpose. Hint, find out how A minus lambda I and A transpose minus lambda I are related. So if we take this part, A minus lambda I, and we find the transpose of this one. So here, because we have subtraction, so that means we can distribute, so this one is A transpose minus lambda I transpose. A transpose is this one. The transpose for the identity matrix, it is just the identity matrix. Lambda is a constant, so there is no transpose, so this will give us lambda I. So now this one is invertible if and only if A minus lambda I transpose is invertible if and only if A minus lambda I is invertible. Because in theorem 6, in section 2.2, we said that A and A transpose, both of them will be invertible if one of them is invertible. So now, since A transpose minus lambda I is not also, so we said this one is the first part. The second part, A minus lambda I transpose is not invertible or this one is not invertible, sorry, is not invertible if and only if A minus lambda I transpose is not invertible. So if this one invertible, then the second one invertible, and so on. So thus, that is a lambda is an eigenvalue of A transpose if and only if lambda is an eigenvalue of A. Because if this one has a solution, that means A is invertible, we can find a non-trivial solution, that means this one is not invertible. If it is not invertible, that means they have the same eigenvalue, which is lambda. So that is, lambda is an eigenvalue of A transpose if and only if lambda is an eigenvalue of A. Because once we solve this one to find the eigenvalue, that means we need to solve the eigenspace A minus lambda I. A minus lambda I multiplied by x is equal to 0. And we know this one, this one transpose is represented by A transpose minus lambda I. And if we can solve the system, we find lambda, that means lambda will be the same for A and A transpose. That means they are related, and the lambda for the eigenvalue and the eigenvalue for A is the same as the eigenvalue for A transpose.